what else is there to say about related rights? It's always a good time. So before we dive right in, let's go ahead and just identify some of the formulas we're going to use today, and we'll call that kind of our toolbox here. What formulas do we have in our toolbox? So we've talked about our cone. So we've got our volume equals 1/3 pi r squared h. And today we're going to focus on the sphere, which is our volume equals 4/3 pi r cubed. And then we'll have the surface area of a sphere. So my surface area is pretty handy. It's just this guy's derivative. So that's 4 pi r squared. And we'll touch on a circle, of course. The area of a circle is pi r squared. Circumference, 2 pi r. And lastly, we'll probably hit on the cube. Volume of a cube is just length times width times height, and since the cube, they're all equal, so side cubed, or length cubed. And then the surface area of a cube, basically you take the surface area of one side, which is side by side, so side squared, and you multiply it by the 6 faces, so 6 side squared. So we have a lot of formulas in our toolbox. We've talked about area of a triangle, Pythagorean theorem, etc., but these are the ones we're going to focus on today. A snowball in the shape of a sphere is melting so that its volume is decreasing at a rate of 5 cubic inches. So again, just watch volume, and it's decreasing at a rate, so that's dV dt. Notice it says decreasing, so we're going to use that as -5. The instant when the radius of the snowball is 4 inches, what is the rate of change of the surface area? So again, rate and surface area, they're asking. So I'm just going to start with my two formulas. Obviously, I need volume since I'm given dV dt. And as you know, volume equals 4/3 pi r cubed. And I'm also going to need surface area since I'm asked for the derivative of surface area. So I'm going to throw that formula up here as well. Surface area, and remember, that's an easy way to remember it. It's just this guy's derivative. So 4 pi r squared. So you'll notice they gave me two pieces of information, obviously volume and surface area, and the question's about surface area, so I'm probably going to attack that part of it last. I know I'm going to need volume first in order to use this, figure out this whole derivative of the surface area. So I'm going to start here. And I know to take the derivative of this because it says dV dt. So real quick derivative, we know dV dt equals 4 pi r squared dr dt. So like we've been stressing for a few days, we're taking this derivative with respect to time. So if it doesn't have the letter t, it gets a d variable dt. I know this is -5 because they said decreasing. 4 pi, my radius they said was 4, so I can throw in 16 here. Dr dt. If I keep cleaning that up, I've got dr dt. I've got -5, divide that junk over 64 pi. Now notice that clearly doesn't answer the question. That gets me dr dt, which I'm probably going to need when I go to get my surface area. So I have the surface area formula. I know I'm taking the derivative because that's what they're asking for. So the derivative of surface area equals 8 pi r dr dt, of course. Again, I'm taking this derivative with respect to time. I'm finding the derivative of surface area, and hopefully now I know everybody else. My radius, they said, was 4, and remember, you just got dr dt, that's why they gave you this dV dt. We can now substitute this in. -5 over 64 pi. And as I clean that up, you'll notice some nice things should happen. The pi should cancel, one on top, one on the bottom. 8 goes into 64 8 times. I can 4 into 8 twice. So it looks like I got -5 halves for my surface area. Now, when we're talking about surface area, of course, we're talking about units squared. So let's just go look at our units real quickly. It was inches per minute, so I'm going to get inches squared per minute. All right, question 2. A stone is dropped into a lake, creating a circular ripple. So let me pause you right there. Just take note of our shape. We definitely have a circular ripple here. It has a circumference that is increasing at a rate of 10 centimeters per second. So hopefully you've caught that that's dc dt. How do I know that? It says circumference. It gives me the word rate increasing, so it's a positive 10 centimeters per second. Find the rate at which the area is changing. So they're asking about, the derivative of area, specifically when the radius equals 20 centimeters. Okay, so you'll notice I'm given two different rates, two different derivatives. I have dc dt, and I want to know about dA dt. So there's two ways you can attack it. You can say to yourself, since I want dA dt, maybe I'll start with that guy's area. But because dc dt is involved, you're probably going to have to do a little work with that bear too. So I'm going to start with area. Area, it's a circle, so pi r squared. Its derivative is dA with respect to time. dA dt equals 2 pi r. dr dt, I can't stress that everything is with respect to time. And do I have enough information? Well, let's check her out. I'm looking for dA dt. They said specifically when the radius is 20. What don't you have? Well, I hope it's obvious you don't know anything about dr dt. And that's why they're telling you something about dc dt. You're going to have to do a little more work to figure it out. So off to the side, I'm going to start now with circumference. Circumference is 2 pi r. I know I need to take its derivative because they gave me dc dt. Again, with respect to time, so the derivative, this is a constant in front of my r, so that's just 2 pi dr dt. And I know dc dt was a positive 10, 2 pi dr dt, so I can easily solve for dr dt. I would say 10 divided by 2 pi is dr dt, and if I want to clean that up, let's just use a little common sense there. Pi is clearly on the bottom, so I could say dr dt is 5 over pi. Now that I have that value, I can substitute that into dr dt. So 5 over pi. Again, take note that my pi's are going to cancel. That's on top, that's on the bottom. 5 times 2 is 10 times 20 should be 200. And since it's area, I just want to check my units there. Shucks, what were they? Centimeters. So I'm going to say centimeters squared per second. And there you go. For our next question, we have the volume of a cube is changing at a constant rate of 75 cubic centimeters per minute. So let's stop where they tell us the volume is changing at a rate, so clearly they're giving us dV dt, 75. Find the rate of change, so we're finding the derivative of the edge of a cube. The edge of a cube is describing the side. So I'm going to say the derivative of the side of a cube, specifically when the side is 5. Okay, so when I have a length of side equals 5. So we might as well just start with volume, since that's what they're asking for. So we said volume is length times width times height, or side cubed. dV dt then is 3 sides squared. ds dt, of course. The question does say find ds dt, given that the side is 5, and we know dV dt is 75, so a really nice friendly question here. So 3 times 5 squared would be 25 ds dt. And so it looks like we're getting ds dt should just equal 1. Second half of the question says find also the rate of change of the surface area. So that's the derivative of surface area when the surface area equals 24. So again, I want the derivative of surface area, specifically when the surface area is 24. So I'm going to start with the surface area formula, which we said is 6 sides squared. And since I want this, I'm going to probably attack that last. I'm going to use the fact that I know the surface area is 24. And that's important because I'm just going to set that equation equal to 24. Therefore, I've got 4 equals s squared. Therefore, the side is 2. Now, of course, technically positive or negative 2, but we're the side of a cube, so clearly we don't want to be negative. Now that I know how big a side is, I can go answer the question I wanted. It wanted me to take the derivative of surface area. So the derivative with respect to time of surface area is going to get me the derivative of surface area with respect to time equals 12s, of course, ds dt. We just discovered, we needed that piece to discover that our side was 2. I've got 12 times 2. And I know the side is changing if I scroll back up here. That was a question we previously found. The side is changing at a rate of 1, so times 1. So the surface area is changing at a rate of 24. Now just keep in mind it's area, so it better be some sort of unit squared. So centimeters squared per, oops, what were we in? Minute. Centimeters squared per minute. There you have it. Talk about tying topics together. Here's a great question that relates our differential equations to a related rate. So, example, the flu spreads among a population of m people at a rate proportional, there's your key word, to the product of the square root of the number of people who had contracted the flu and the cube of the number of people who have not contracted the flu. If F denotes the number of people who have contracted the flu, write a differential equation that could be used to model the situation with respect to time, where K is the proportionality constant. It sounds a lot tougher than it is. Let's just break it down. M represented our population. Okay, we had a population of m people. F denotes the number of people who have contracted the flu. Write a differential equation. So again, we're getting a differential equation, so an equation with a derivative, that could be used to model the situation with respect to time, where K is the constant of proportionality. Well, keep in mind, if F people contracted the flu, how many people did not get the flu or come in contact with the flu? I would say it would be the population minus the amount that did. So I'm going to say M minus F did not contract the flu. All right, now again, I told you, you've got to look for that word rate proportional. That's what gave it away. We spent a whole day doing topics that were rate proportional to another. So it says, the flu spreads among a population of m people at a rate. So I'm going to say that is dm dt. They told us with respect to time. Proportional, when you see that word proportional, that's equal to your K, your constant of proportionality. And here's what it's equal to. It says the product of the square root of the number of people who have contracted the flu. So I would say that's the square root of F. And the product of that and the cube of the number of people who have not contracted the flu. So M minus F cubed. And all they wanted to do was to write this differential equation. Now perhaps if you just totally copied that and I did all the work for you, you need to just pause it, rewind this section, and try it again. This is a big deal that when you catch rate proportional, that we know it's, something you got to slow down. It should be something is equal to K times something else. And they'll tell you exactly what it is. The rate of population, which was M, and the product of these variables here. Well, that does it for us tonight. Have a great night, and we'll see you tomorrow.